Right, guys, now that we are masters of finding vertical and horizontal asymptotes for these rational functions, basically what I can tell you is it's going to be really easy to compose a graph of them. So what we're going to do is we're going to identify the domain which goes hand in hand with our vertical asymptotes. We're also going to identify the horizontal asymptote and work from there, just finding some extra points on our graph and sketching what we need here. So first things first, let's take a look at what the domain of this would be. Because our denominator here is only 0 when x equals -2, we should certainly remove that from our domain of our function here. So we have -infinity to -2 in union with -2 to infinity, but we use a parenthesis here to exclude this -2. It's the only thing that we're not going to include. And so that being said, we can go ahead and identify that we're also going to have a vertical asymptote at that undefined value. So the first thing I'm going to do is I'm going to put this on my grid here. And yes, you need to label this every single time. So we're going to say that this is at the x value -2. Now in terms of horizontal asymptote, remember we just looked at the degree of the top compared to the bottom. And I noticed that we have a 0th degree over a 1st degree. So bottom heavy basically always implies that it's just going to be y equals 0, or I actually do appreciate when people write this, the x-axis. So I'm not going to not make my horizontal asymptote here, but I'm also not a lazy man. I just want to tell you that if you don't want to draw a dotted line over your horizontal or your x-axis here, you can just write y equals 0 on the outside, and I would believe you that there's an asymptote there. So given that our graph exists everywhere except for at x equals -2 here, and we know that out on the ends we're just going to get really close to this horizontal asymptote, you could already see that there are several different types of graphs that could exist, this and this, this and this, or we could go up and then down, or how about down, oh, you guessed it, up. The thing here is this: we basically just need to find some extra points on the graph to see where our graph would exist. And remember that our graph isn't really interesting out here on the sides. It's only really interesting around here, in and around its vertical asymptotes. So that being said, we're going to table some values here. But before we do that, one thing that I want to mention is you must, that's pretty demanding, isn't it, always find the x and y intercepts for me on these graphs, because it's just best practice. Now, taking a look at this, if we want to find the x-intercept, recall that we set f of x or y equal to 0, and we answer this question, well then what would the x value have to be? So this is a pretty key concept, but when you set this y value equal to 0 here, and you say, well, this is equal to 1 over x plus 2, what I want you to consider is that a fraction only ever equals 0 if the top equals 0. The bottom or 0 be undefined, top equals 0, the whole thing's 0. So here's the deal. When we find the x-intercepts, we basically set the numerator polynomial equal to 0 and solve for its zeros, which this is fun for me, because when I set 1 equal to 0 and ask this question, hey, what can I plug in for x that's going to cause 1 to equal 0, I get a lot of blank stares, and the reason why is because you're never going to cause 1 to equal 0. So here's the deal. We say that no x-intercepts exist, none. And that's okay, we want to write this here. Now, why don't they exist? Well, one big reason why is that we have a horizontal asymptote here. But I don't want you to get the impression that we can never cross a horizontal asymptote. You could actually have some weird graph that, sometimes we have graphs that do this here. It's really crazy. And we would have something that is actually defined at y equals 0 at some point. It's just that most of the time we're going to get some branches that don't exist at our horizontal asymptote. But set the numerator equal to 0, solve for this y-intercept. We set x equal to 0, of course, set x equal to 0. And this is pretty neat, because in your function f of 0 just means everywhere that you had an x, it'd just be a 0. We get a half. Okay. So a half here is our y-intercept, and we should go put that on our graph. I'm going to switch over to blue here. So that being on our graph here, here's the thing. You should label it on your graph. But because I don't want to crowd this up with everything, what I'm going to do is I'm actually just going to include it in my table and say that you'd be okay if you put this on your table over here. So what we're going to do is we're going to table some values, and because our graph is only interesting in and around its vertical asymptotes, the rule is this, and I hope you're listening, 2 to the left of and 2 to the right of every vertical asymptote, we're going to plug those x values in. So because this is -2, we'll do -4 and -3. We don't have to do -2, it's undefined. -1 we should do, and the neat thing is we've already done 0 as a matter of coincidence. So the neat thing about rational functions is that they are indeed ratios. So that means that you're always going to get a fraction for an answer. And so if you're not writing these as fractions, you're crazy. You're crazy. Because I'll tell you what, these are both polynomials, top and bottom. And what we'll do is we'll just go plug these all into the top one. and then go plug these all into the bottom one, and then we'll go back and evaluate, because then, see, you're taking your time and you're being careful when you craft these. So the neat thing about this is, when I plug these all into this polynomial, at least the top polynomial, there is no x, and so I'm always going to get 1, 1, 1, 1. Now on the bottom, I get negative 4 plus 2, which is a negative 2. So you can see here that I get a negative a half. When we plug in negative 3, I get negative 3 plus 2, which is easily negative 1. Now I'll evaluate this, negative 1. And then when I plug in a negative 1, I get negative 1 plus 2 is a 1. Okay, that's really easy to do. I'll tell you it's a 1 now. So we get these values right here, negative a half, negative 1, and 1. Kind of hard to see, sorry about that. But we're just going to go graph them now, and be careful. Remember, you leave from the origin. So like 0 half, it's on here. Okay, negative 1, that went to a height of 1. So that would exist right there. Let's see, negative 3 will go left 3, and it looks like we go down 1, so that would exist here. And then left 4 down a half. Well, left 4 down a half, you can see that's right here. You would see that there's some level of, like, you know, like symmetry here. It's kind of like origin symmetry, even though it's not around the origin. It's not origin symmetry. But it is kind of like origin symmetry around where your asymptotes meet, if that were the origin. So a weird thing about this is, in terms of shape, inevitably you're going to draw this graph so close to your asymptote that you're going to be like, well, it's not supposed to touch that. But what I'm telling you is, it's okay if it touches it on your paper, and we'll just pretend that it doesn't, and that we're saying that, oh, it's just so close you can't tell. But you have to label your asymptotes. As long as you do this for me here, then as long as you draw something like this, I'm cool with it, okay? Don't draw something like this. That would be like you sneezed or something. We want to draw really close to vertical asymptote. So, hey, pretty easy graphs to draw once you get your vertical and horizontal asymptotes here. So let's take a look at another example here, a little bit more exotic example. And this one is really near and dear to my heart. I hope you're paying attention to this one, because it looks like something where we actually are required to factor the top and the bottom first. We have some substance here. So we have x times x plus 3, and the denominator here we would have, looks like x plus 3, x minus 2. So one of my favorite things happens here. Our common factors on top and bottom cancel out. And yes, you should write, we're going to say equals down here, we're going to write x over x minus 2. Now I want to box this, and I want to ask a question. Is this the same function as the original function right here? And one would be inclined to say yes. But what I'm going to tell you is, when you look at the zeros of your denominator in your original function, the zeros are positive 2 and negative 3. That means that if you plug in either of those numbers, boom, undefined. So in terms of domain, let's write our domain here. It would be negative infinity up to our first 0, which occurs at negative 3, in union with negative 3 on the interval up to 2, and then we would say not including 2, and then not including 2, and going out to infinity here. You can see that we get 3 defined intervals for our function here. But the crazy thing is, I'm actually going to graph both of these functions now. We have x squared plus 3x, x squared plus 3x. Let me go over to Desmos here, and we'll get some of our stuff out of the way, some of my stuff out of the way. So x squared plus 3x, we want to compare this to the other graph. Y equals, parentheses, x squared plus 3x, all over, and then we had x squared plus x minus 6 is what we had here. So the interesting thing is, we see that our domain, hey, doesn't exist at negative 3 and positive 2, because those are the zeros of the original. But when you look at where we have a vertical asymptote, crazy, it really only exists at the zeros of our simplified form of this function here. And so we can see that we have a vertical asymptote at x equals 2 right here, and we don't have a vertical asymptote at x equals negative 3. So what's up with this? What's up with this? Well, what I want to tell you is, if I were to scroll my mouse over here, check it out. It's really, really subtle here. Boom! We get an undefined spot. So what this means is, our graph actually doesn't exist right there. What I don't like what Desmos does is it makes me put my stupid mouse there to see this dot. It looks like it's a continuous graph, but look, it's undefined here, because if you plug in negative 3, you're going to get an undefined value. So really important to me that you recognize that it is undefined at that value. But when you talk about where do your vertical asymptotes lie, we're going to remember that they only lie at the zeros of our simplified expression here. So we would say that our zeros here are x equals just 2 in this denominator expression here. So we get x equals 2. And we're just going to put that down here for our vertical asymptote. X equals 2. As a matter of fact, let's go put it on our graph right now, because we're all just super excited that we just found the vertical asymptote. So x equals 2. Let's talk about our horizontal asymptote. We have a balanced degree, and so we're going to have a ratio of our leading coefficients, y equals 1 over 1. And so that's really what? 1. We'll go put this on our graph. So we say at y equals 1, we have this horizontal asymptote right here. So we're on a roll. Let's go ahead and find our x and y intercepts. X-intercept, you set y equal to 0. So should I use my original function or the simplified? The neat thing here is we could actually just use the simplified one for everything except for the domain. We have to use the original one's denominator here. And so we would see that this right here, it's x-intercept, if we were to set y equal to 0, remember that this is only going to happen if the top equals 0. So you might as well not set this whole thing equal to 0. Remember that we set the top equal to 0. And it looks like at x equals 0, we're going to have an x-intercept. So I'm going to put this on my graph. Kind of stupid question, but what's your y-intercept? Well, it'd have to be 0. But let's go find this. We'll plug in 0 for x. We see that f of 0 here, using our simplified form, it's not going to matter which one you use, is 0 minus 2. We get 0 over negative 2 here is 0. So why is it that I can use my simplified one here instead of the original function if they're not really the same function? Well, they aren't really the same function, and let me show you why. If I were to graph x divided by, and we had what? X plus 2, I think it was. Well, it must be minus 2. Over x minus 2. The thing here is these two graphs overlap everywhere. As a matter of fact, they behave so similarly except for at one value. And that one value is at negative 3. I turned off the first graph, and when I go over to negative 3 here, I can skip right over that because, well, it kind of lacks that other factor in the denominator here. So because these two functions are not the same function, but because everywhere they behave the same except for at one spot, then we could use the simplified form of this function to determine our x-intercepts, our y-intercepts, our vertical asymptotes, our horizontal asymptotes. Again, the only reason we use the original function denominator zeros is to find our domain, and therefore one thing that I do want to write here is that we're going to have a hole in the graph. A hole in the graph when factors cancel. Okay? So when we get canceling factors, whatever the zeros of those factors are, like the 0 of x plus 3 is negative 3, you're going to have a hole in your graph at negative 3, and that's one thing I want to write here. Hole at negative 3. And you got to know how to find these things whenever you have canceling factors. So all of these things being said, hey, you guys, all we got to do is tail out some values. This is so quick at this point because we know we can just use the simplified form of this function. It behaves the same way. So in terms of our vertical asymptote, 2 to the left, we'd have 0. 0, I'm going to go ahead and put that on my table. I should always put on my y-intercept. And then I'm going to say, well, 1, and I suppose not 2, but 3 and 4. And then we're going to add one more value here. It's kind of a nebulous thing, but we would say that whenever you have a hole in your graph, I still want to plug this into the function that was simplified just to see where the original function would have been at that point, because what we're going to do is we're going to put a hole or an open dot. So in this case, we have a fraction, a fraction, a fraction, a fraction. Okay, let's do all the top values first using the simplified form. It's just x. So whatever your x value is, that's what your numerator is going to equal on all of these. Beautimous. Now looking at the basement here, we have input minus 2. Well, we have 1 minus 2 would be a negative 1. So this simplifies to a negative 1. When we look at 3 over what? Well, we plug in 3 here, we get 3 minus 2. There's some more room there. 3 minus 2 would be a 1, so we get 3 over 1 is 3. Plug in a 4 here. 4 minus 2 is a 2, so we get 4 over 2. That simplifies to 2. And if you plug in a negative 3 minus 2 is a negative 5. So this is kind of fun, but we get 3/5. And I would actually advocate for whenever you get something like this, where you don't know exactly where it's at, just go get a decimal on your calculator, which in this case, we actually get 0.6. So all I'm going to do is I'm just going to go put all these points on my graph. So we get 1, negative 1, 1, negative 1. Let me switch back over to purple here. We had 3, 3, so right 3 up 3 from the origin. We had 4, 2, right 4 up 2. There's our branches right here. And then very importantly, we have to put on negative 3, 0.6. But what we're going to do is we're going to put a big fat open dot right there. And so what this graph looks like is this guy right here. It's kind of, I missed it there a little bit. But we'd say, there she is. Beautiful. Okay. So I want you guys to use this to help us find some asymptotes on this, except for this time, I want to notice something here. We have a top-heavy equation. So let's take a look at an example here that doesn't have a hole in it, okay, and it's not a really basic graph, but we're going to look at a situation in which we have a slant asymptote specifically. So let's start with our domain. Our denominator would be undefined at x equals 0, and so the very first thing we want to write here is that our domain is all real numbers except for 0, and also that we have a vertical asymptote, therefore, at x equals 0. Now, one thing that I should have done, and shame on me, is this. I should have factored the top and the bottom first here, like so. So we get that. It's over x. Sorry about that mess right there. But anyways, nothing cancels out, and we can proceed with what we've got here. Now, horizontal asymptote, what you can write is none. And the reason why is because we have a top-heavy situation. So this top-heavy situation, what we want to find is our slant asymptote. And to find a slant asymptote, you have to divide. And to find this, you're actually going to have to, I guess, long divide here. So we get x squared plus 0x minus 9. And we get an x out here. And the coolest part about this is I just want the quotient, you guys. So check this out. How many times x go into x squared? I think last time I checked, it's x. X times x is x squared. If I take that away, I just get nothing, and I drop down my 0x here, minus 9. And I ask this question again, how many times x go into 0x? Well, nothing. So what's the quotient? Well, this. Well, what's the remainder? Don't care. I just want this. So we would say that our slant asymptote is at y equals your quotient, which was x. Not always y equals x, but in this case it is. So let's just go put our asymptotes on here. We would say that one of these is at x equals 0. I'm just going to say that's our y-axis here. I hardly need to color on this because we just say x equals 0. And if we look at the x-axis, or excuse me, the slant asymptote, we would say that it's a line, y equals mx plus b, so it hits at 0. Okay, and it goes up one, right one. I always like to just put little notch marks at where I would have put my dots for my line anyways, and that kind of gives you a little asymptote here. But here's our slant asymptote at which our graph is going to drive its car when we get to really big or really small x values here. I feel like I can't see this middle asymptote here. Anyways, at this point, let's find our x-intercepts. X-intercept, of course, we said y equal to 0, but remember, only equals 0 if the top equals 0. So we would say the zeros of this right here would be plus or minus 3. So our x-intercepts, we have 2 of them. X equals, I'm not going to write x equals, so we'll just write plus or minus 3. I'm going to go put a dot at positive 3, and I'm going to go put a dot at negative 3. So our graph hits there and there. And for our y-intercept, remember, we plug in 0 for x. We say f of 0. It's really 0 squared minus 9 over 0, which is, oh, well, wait a second, undefined. So why is it undefined? Well, last time I checked, that was our undefined value. So all of these things being named here, our y-intercept doesn't have one. We're just going to go table some values. And again, it's a fraction, you guys. It's just a fraction. So we're going to plug into the top and the bottom separately. We'll go 2 to the left of and 2 to the right of our undefined value here. So we'll go negative 2, negative 1, 1 and 2. And given the choice of plugging it into this factored form of the original, I actually kind of feel like plugging it into the original expression this time is a little bit more succinct. So let's plug these all into the numerator here. Negative 2 squared minus 9, just because I know that I have some people, I'm not going to say it's lazy, but they don't use parentheses, and they try to tell me things like, well, negative 2 squared is a negative 4, and I'm like, check it again. It's a positive 4. So we get 4 minus 9. We get negative 5. As a matter of fact, I don't know if you noticed at the top of this function is even. So when I plug in 2, 2 squared minus 9 is also negative 5 because I get 4 minus 9. So let's plug in negative 1. Negative 1 squared, well, that would be 1 minus 9 is negative 8. And then 1 squared minus 9 would be a negative 8. And so let's look at our denominator values now. So plugging all these in, it looks like we just get the x value that we're plugging in down in the denominator. So we get over a negative 2. Here I get over a negative 1. Here I get over a 1. Here I get over a 2. Basically, I do want to simplify all of these, and if I get a decimal, then so be it. So up on the top here, I get 2.5. Here I get 8. Here I get negative 8. And here I get negative 2.5. So when we go put these on our grid here, we say negative 1, up 8. That's clear up here. I got another point here, left 2, and it went up 2.5, so that's about right here. If I go right 1, I go down 8, as a matter of fact, and I go right 2, go down 2.5. Overall, this is an odd function here. But we say, what would this graph look like? Now, I got to tell you, When you have a slant asymptote, it's one of two possibilities. I'm even going to go green. You guys are really going to see this here. So either our graph gets really close to the slant asymptote from the top out on the end and rides up to positive infinity here at our vertical asymptote, like it does actually on this graph, and starts way down here at negative infinity and rides up on the bottom of this slant asymptote, which I could have done way better getting closer to them. And so either that, or what happens is we come up from the bottom of the slant asymptote, and this would have no choice but to diverge to negative infinity, and we would get this middle looking graph right there, which, hey, we don't get on this one. But in terms of, or with respect to slant asymptotes, it's going to look like one of those two possible types of hyperbolas there. So use these as kind of examples to help you out on normal graphs, on graphs where you have a hole in the graph, on graphs where you have a slant asymptote. Be the masters of hyperbole. Cheers.